Alright, here we go. This video is about reaction rates and things that make chemical reactions happen more quickly or more slowly. So let's start with temperature. Temperature is going to be pretty easy to understand, and rather than writing a bunch of words in this video, I'm going to try and use as many pictures as I can, or as many drawings. So let's just say we've got this container here. And let's say we've got reactant A, maybe it's an atom or a compound, who knows what it is. And let's say we've got reactant B. And let's say that the temperature is low. So these guys, they are going to be moving. They're just not going to be moving very fast. They're going to go about their random directions, eventually maybe bounce off the side and do their thing. But they're both, the chances of them hitting each other eventually is pretty high. But how could we make them hit each other sooner? What we could do is we could take that temperature and we could turn it up. So if we turn the temperature up, then what's going to happen, they're still going to bounce around randomly. They're just going to do it a lot more quickly. They're going to bounce all over the place. So maybe this happens, and then maybe they hit right here, and we get our chemical reaction. So if you take the temperature up, your reaction rate goes up. If you take the temperature down, then your reaction rate goes down. So think about it. Why do we put food in the refrigerator? That affects the rate of our food spoilage, right? Okay, so there is temperature. Okay, so next up, surface area. Also pretty easy to understand. So let's say that we've got two pieces of paper that are identical. We take one and leave it flat. We take the other piece of paper and we crumple it down into the tiniest ball we can. So if we come up to each of these pieces of paper with a match, they're both going to burn, but one of them is going to burn more quickly. And which one's it going to be? You know that it's going to be this one that's going to burn more quickly. Why is that? Well, look at all of this surface area that's exposed to the air particles that are in the room. So if you were an oxygen particle and you were going to burn with this paper, very easy to get at so much paper at a time. And if you were an oxygen particle around this one, how much paper can you get at? You can get at just this small surface area that's exposed. So if you take the surface area up, then your reaction rate can go up. So that's a direct relationship. If you take the surface area down, then the reaction rate would go down. So that's surface area, pretty fast. So cruising right along here, let's go to concentration. Concentration means that if you think about it, a reaction will happen much faster. No, that's not true. Concentration in chemistry, what that means is that you're changing the amounts of something in a reaction. Let me do this. Let's say we've got a beaker and we've got it filled with water, let's say, and in that water we've got, let's do this. Let's say we've got this chemical and what other chemical in it? Let's say this chemical. That's not very good colors, but oh well, we're going to stay with it. So if these two guys were in the water and they're moving around randomly in the water, they're going to hit each other eventually, right? It sounds a lot like the temperature one, doesn't it? But what would be a way that we could increase the chances of this reaction happening? Well, if we added a whole bunch of these, the blue ones, or even if we added a whole bunch of these, the black ones, then what happens to the chances this reaction is going to happen? Well, the chances that they're going to hit each other are going to go way up. So if you increase the concentration, then the reaction rate is going to go up. Likewise, if you were to remove some of these, if you took the concentration down, then the chances of these guys hitting each other, the blues hitting the blacks, the reaction rate would go down. What would be another way you could do that? I guess you could, you could add some more water. If you added more water, then it would be more dilute, and these guys would be able to spread out more. So that would slow the reaction some. So 3 down, 2 to go. Okay, pressure. Let's see here. Pressure happens, it affects rates that of reactions that have gases involved. So let's say we've got this airtight container, and let's say that the top of it is a piston that can slide. So like there's a handle right here, and this whole thing, if you push on it down, you can make this container right here, you can make this container smaller in size. So let's say that we've got some kind of a fluid in here. Let's say we've got some water or something in here. And let's say inside the water we've got this reactant. And let's say out in the air, up above, we've got this reactant. What is it? Who knows? So out in the air here, these guys, they're flying around, bouncing off of the container, maybe some of them bouncing off the surface of the water, maybe some of them even dissolving in the water, but I'm going to ignore that. So what are the chances, the way that this is drawn, of one of these blue ones hitting, or black ones hitting one of these red ones? Well, it's going to happen eventually, but how can I make the chances of that happen, how can I make the chances greater? Well, what I can do is I can take my my handle here, I could push this down, and what's that going to do? I'll be back in a second. So by pushing this down, by taking the pressure up, what I've done is I've made it so these particles have a much, much higher chance of interacting along this surface here. So if I take the pressure up, then the chances are much higher that my reaction rate is going to go up. Likewise, if I took the pressure down, then you would think that the reaction rate would go down. And that is pressure. 1 to go. Okay, so I'm going to do 2 examples here. I'm going to talk about a catalyst. Let's say that you've got a bottle of hydrogen peroxide, and let's say you throw in a tiny little speck, a little grain, a little tiny piece of something called manganese dioxide. What happens is that manganese dioxide is a catalyst that breaks this hydrogen peroxide, it breaks it apart into 2 things. Whoops. Oh boy, what did I do? I hate it when I do that. It breaks it apart into plain old water, and some oxygen gas comes out. So there you go, your hydrogen peroxide is ruined. But the neat thing is, or I don't know if it's neat, but the interesting thing is that this manganese dioxide isn't destroyed in the reaction. So after it does this to one peroxide molecule and makes water and oxygen, it can just do it over again. So this same manganese dioxide particle can just go and find another peroxide and wreck it, and then find another one and wreck it. So if you just put in one tiny little piece of manganese dioxide, your whole bottle of hydrogen peroxide is ruined. So since manganese dioxide isn't affected by the reaction, we call it a catalyst. Its formula doesn't change. In the reaction. In other words, that's the same thing as saying it isn't changed in the reaction. Okay, I'm going to keep this under 10 minutes, but check this image out. We're not going to go deeply into biology because it gets pretty crazy kind of fast here, but take a look. Right here, this is our enzyme, this gray circle. So this is a big molecule. This is an actual, it's a big chemical. And they draw these simplified sketches of them because they're so crazy you can't draw them if you try and draw every atom. But anyway, this enzyme, its job is to take this chemical, whatever it is, and its job is to take it, grab it, and then break it into these 2 pieces. So that's what its job is. So this enzyme does this to this. And then the enzyme keeps its same shape that it had before, and it can go out and it can find more of these and do this to it. So that's the catalyst. But what happens if this other weird chemical, this weird shaped chemical right here, comes along, and it happens to be able to lock in right here, and when it does that, it blocks this area where it was supposed to grab onto this other particle. So now this enzyme, it can't do its job, so this thing doesn't get changed into this. So that's called inhibition. So if something helps a reaction go faster, we call it a catalyst, and if something slows a reaction down or even stops it, we call it an inhibitor. And since I'm under 10 minutes, let me just see if I can Google a picture of some different catalysts and show you how crazy they are. So I just Googled enzyme atoms. So take a look at these things. These things are bananas. Just look at, let me just click on one of these. How about this one? So imagine trying to count all these atoms. This enzyme, what is it? It says it's asparaginase enzyme molecule used in I'm guessing leukemia, chemotherapy or something. But anyway, that's how complex enzymes are in biology. It's pretty bananas. Anyway, there's my video on reaction rates.